Hi, it's me again. So now we'll discuss about nonlinear programming with constraints. I intentionally put this as the last part of the lecture simply because we require computers to solve this numerically. It's very difficult and time consuming, also very prone to mistakes if we do it manually. So I'll just explain the concepts, and then we'll skip some of the details which you can learn from it online. We'll talk about GRG method. Excel has this method. We'll talk about successive quadratic programming. I've touched this a little bit on the Lagrange example. And then we'll talk about the interior point and some penalty function. I think because this method is obsolete, we're not going to use this. This is not used anymore, so we're not going to explain this any further. So GRG method is more like the a simplex method in linear programming. So it goes through the vertices of the constraint and then evaluate the objective function based on that. It's more also looks more like the direct substitutions, where we have our if we substitute x1 equals to something x2, like in our case, in the previous case, that means x1 we see that as a dependent variable of x2, and x2 is then becoming the independent variable where we can vary. So in this case, so if we suppose that x1 is the dependent variable and x2 is then independent or non-basic variable, so x2 is then something that we can vary. So we find then if we have this, for example, the constraint, right? So we have the constraint. We derive the constraint, and then equals to 0, and then we get the x1 equals to something in the form of x2, and we put that the x1 back into the equations of the objective functions, so we get this. This formula in the bracket is what we call as the reduced gradient. So we know now x2 is our independent, x1 is dependent variables, and then this reduced gradient is then the df dx1, which is in this case df dx1 minus dh dx1 transpose, yeah, and then the dh dx2, and I in this case is then independent variable, which is then the x2, and then d is the dependent variables, which is then the x1. If we then make this is then the general formulations, yeah, it's basically we have the constraint of h, and we derive the constraints as a to the independent variables, and then we also derive the constraints to the dependent variables, and then these dependent variables we can then make it as a functions of independent variables, yeah, and then we put them all together back into the objective functions, and then we get the GRG algorithm. So now we have to then select, in this case, what are the independent variable and what are the dependent variables, xt. So calculate now as the initial guess, with the initial guess x0, we calculate the fx0. We can calculate the reduced gradient gr. So the reduced gradient is then the derivative of objective functions to the independent variable. Yeah, and then we put them into these equations, and then so determine, and then the second step is then determine the search direction for x independent in lower limit and upper limit. So this x has to be in between the upper and lower limit, yeah, and then and then we do a search direction for dependent variable SD, and then we calculate then the new x independent with the lambda and the step, and also we calculate the new dependent variable with the lambda and then the step, and then we find the lambda with the necessary condition of df d lambda equals to 0. We'll see that, and then we do this over and over again until we satisfy, until we satisfy our convergence limit. So let's see. Now we have this objective functions, very nonlinear. So we have one equality constraints linear and another nonlinear. Yeah, so now we have like 3 variables, 1, 2, 3, and then 2 equations. Yeah, so that means we have 1 degree of freedom, and so if we start from 0, 1, 1, just take any arbitrary number. So fx1 equals to 2, h2 equals to 5. So we satisfy this constraint, all positive. That means this is then the feasible number. We put this back into the equations of f. So we get fx0 equals to -3. And as I said, so we have 1 degree of freedom, means we have 1 independent variable. So assume that x3 is then the independent variable. So you can just assume a different x, and then x1 and x2 will be the dependent variable, and then we derive f to x3 or xi independent. We calculate the reduced gradient with this formula, and then the df dx independent is 2x3, because 2x3. So we derive this into x3, 2x3, so you get over here. And then we derive the f to xd, which means to dx1 and dx2. We get these equations. And then we derive dh, the constraint into dependent variable. So we have, since we have 2 constraints, we have to then derive it h1 to x1, h1 to x2, h2 x1, and h2 to x1. So we have this matrix, and then dh dxi independent, we have only 1 independent in this case, so we derive h1 to x3, h2 to x3, and we have this matrix. And we plug in this whole into the reduced gradient, and then we put in this number, so we get this results. And then the first step, we can just assume that the first step is then minus this gradient, which is this minus, and then the step for the dependent variables is then we use this formula, and we get, this is then the results. And then the new x is then the old x plus lambda times the step. So since we know already the step, and then we plug in the numbers, and then we have this, we have them as a functions of lambda, and then we put this xi and xd back into the objective functions, with lambda in it, and then we then derive this into its first derivative, makes it into 0 to get the value of the lambda, and then we go back, the value of lambda, and then we go back, we calculate the new x1 and the new x independent variable, and then the new dependent variable. If we see now, if any of these is crossing any lower bound, for example, and then we have to then set them to 0, or in this case, if the lower bound is then has to be positive, you have to make them back to positive. If the lower bound is then 1, that means we have to make this into 1, that means make this into 1 as well. Then we check the constraints with the new data. So we see that we put them back, all of these are not feasible. So we have to recalculate the new variables. In this case, we have to calculate the new x1 and x2 because they are dependent, remember, while x3 is independent variable. So we keep x3. So x3 in this case we keep it as 0.4588. So x1 and x2 we calculate them back, and then we get this 0.619, 0.923, and the f of these values is minus 6.5. So we repeat this step again until we converge to the solutions that we want. So GRG is normally very slow in convergence because due to step 4. Because this check, we are now checking if the obtained variables are feasible. If not, then we have to recalculate the dependent variables based on the values that we have in the independent variables. Because of this, it's very slow, but its performance is robust. Some of the computer codes using GRG is we have GRG2 and GRG by IBM. We have Minus as well. We have this Geno Simulsolve, which I don't know what these two are. In GAMS, GRG is implemented as Minus or CONOP. So Minus is then GRG1 and CONOP is GRG2. So we're using the same equations. You can see that we have variable x1, x2, x3, positive variable x1, x2, x3. We have equations h1, h2, and the objective function. So we want to minimize f by using the in this case minus. So the value is then minus 7, the optimal solutions. We use Excel, so you can see now GRG nonlinear. So use x1, x2, x3, and then the objective function is then this one, h1 and h2 has to be equals to 2 and 5. So we put in the formula of x1, x2, x3 into f, h1 and h2. We use GRG nonlinear, and then we just put the constraints that this first constraint equals to 2, b9, and then b10, second constraint equals to 5. All of them has to be positive. We have to change variables x1, x2, and x3. We solve it, and we get minus 7 as the answer. Now, successive quadratic programming. The basic idea is that we have nonlinear objective functions which we have to replace by its local quadratic approximation via Taylor expansion, and we replace the nonlinear constraint with local linear approximations. And then we apply the Newton-Raphson method to solve the Cauchy-Kontaker, the Lagrange optimization for the modified version of the problem. So suppose that we have now fx, hx, gx, and then we have the step s as delta x, and so the modified objective function in this case is then using the Taylor expansion. So we have modified f is then the first derivative of f times delta x, s, right? And then plus half times delta x, or the s, times the second derivative. S is the second derivative, and then times s. And then the subproblem, the subproblem in this case is then we minimize, so this minimize has to be here. So minimize the modified subproblem, and the constraint, the HA, is then we approximate it to its local value. So we have the HA, the modified one, equals to the HI at point x times the HI times s, which is then the delta x, the first derivative, and same goes to the inequality constraint. A here is then the approximation. So we have now a linear one, while in the objective functions, because we have the multiplications of the x over here, delta x or ss, this makes the nonlinear objective functions. So now we have nonlinear or quadratic objective functions and linear constraints, and this recalls to the Lagrange or Karush-Kantaka equations. So that's hence the name successive quadratic programming. So the algorithm is then, so we just have to use any x0 and then set the initial second derivative of the objective function. You can either make your own B0, or you set B0 as matrix identity and then evaluate fx0, g0, and hx0, and then also we evaluate also the first derivative. In this case, at this step, xk equals to x0. Now evaluate the second derivative, the first derivative of the objective function, the inequality constraints, and then equality constraints, and then the b, we don't update it yet, and then now we solve this problem, the modified problems of objective functions. So the first derivative, we have it already, times s, which is delta x, and then times this plus times s times b, the initial Hessian matrix, and then s, and then we also modify the h and then the g, and then using the KKT condition, so we sum them all and then makes them equals to 0 as the first order conditions of the KKT, and then we multiply the Lagrange multiplier u to the inequality constraint equals to 0. This has to be equals to 0. This has to be a positive number, or this has to be 0, and that is not 0 for the non-binding. And this has to be equals to 0. That has to be less than or equals to 0. And then now we introduce another variable alpha. In such a way that alpha is then a fraction, and then a penalty function, so xk plus alpha s, and less than or equal to as a function of x, the previous k, and then where p in this case is then the f, the objective functions over here, plus the lambda j. Right, so depending on how many constraints j that we have, we can have as many lambda as possible. Then we solve this, and then we use the first derivative to get the lambda and put that lambda back into the equations, and then we calculate the new x, and then that new x becomes the we calculate again the whole functions, and we repeat the whole algorithm again. The same equation. So if we have these equations, objective functions, we have this h, we have this g, and then we start with x2 and then 1. We calculate the f0, h0, g0, shows all feasible, and then we do the first derivative of f, second derivative of f to x1 and x2. So we put them as the initial, the Hessian matrix, or we could also use matrix identity. I think this is all. And then the first derivative of f, the first derivative of g, and we put them all in here in the equations, and then we do the first iteration, and then we get this as the functions of s, and then h, this, and then g, which is this, and then KKT. Apply KKT or solve manually to combining HA and SG above. You can here, you can solve for S1 and S2, and then so for KKT, for example, so you have this equals to 0, that one, this one, and then now you can know if you assume for binding for J, that means this one is 2 equals to 2, and then we solve all of these equations together. We get S1 equals to 4, S2 equals to -2, W equals to 0, and then U equals to -8. So since U cannot be negative, so this inequality constraint is dropped, so U has to be equals to 0. And then we solve it again, and we get this new number. and then this new f. Yeah, so if we implement these GAMS in SQP, implement SQP in GAMS, it is implemented in the code called SNOP, S-N-O-P. The same equations, so so we know that the f is now, the result is 5, and then x1 is 1 and x2 is 2. Some comments. Hessian matrix or its approximation has to be calculated. Yeah. There is no enforcement for it to be positive definite, so it can be anything, because it can be updated and updated. So depending on what is then the approximation for Hessian matrix that we are using. And then the correct selection of active inequality constraints is also required. It is faster as it has second order convergence, and it typically requires fewer functions evaluation. So you can see it's only like how many iterations? Only 5 iterations. And then it can go infeasible, yeah, because it can crash the engineering models, more sensitive to noise. And then if we terminate the optimization before reaching the optimum, SQP does not guarantee that we'll have better solutions. Last part is then the interior point. So interior point is basically we add a barrier function in this case. So we have fx, so fxx. So we introduce the barrier functions. So the details of this part we can find it in this website. So so if we introduce this barrier function, it hopes that we can get to the solution as close as possible. For example, in this case, so we have fx in this case, and then mu ln x is then the barrier functions. So we have, if mu equals to 10, we have this number. Mu equals to 5, we get that. Mu equals to 2, we got this. 1 equals to that. And if it's unconstrained, if we know that the minimum value of this is x equals to 3, so x equals to 3. So the smaller the barrier functions over here, the mu, we get to the solutions. Closer and closer. The same goes here. So we are moving now from here to there. Yeah. How to solve it? So we could also use the KKT problem. So we have this original problem. So we have the first derivative equals to 0 with this constraint, and then we define z as 1 over x, and then solve the modified versions of KKT. So instead of having this in the barrier functions, we can have this. And then solve it with Newton-Raphson method, which you know already, and the KKT. And then find a search direction. So if we have these examples, I think you can see this online, yeah, or read this lecture. So we have this starting point, and then rearrange this, and then we solve for dzk to get the step. And then the step size, yeah, you can see, you have seen this, that is then the merit function, and then we put that back in to calculate the new x, and then the new lambda, and then the new z. Yeah, and then the convergence criteria, yeah, you can set whatever you want, like either this or that or here. The overview of this interior point method is that we initialize the initial value of x, lambda 0 and z0, and then we solve this Newton-Raphson of the KKT, and if it's converged, and then we have optimal solutions. If it's not, and then we do the search directions by using this formula, and then we backtrack we update the solutions k plus 1 of x, lambda, and z, and we go back again to find the to compare the solutions to the previous one. You can do these examples on your own. So penalty functions, I think I can skip this. So some recommendations for constraint optimizations, I took this from Bigler slides. So best kind of algorithms is then GRG2 or CONOPS. minus SQP, and IPOPT. These four are best depending on your situations. GRG is slower but robust, we know with it, but for small problems we can use SQP. For large problems with mostly linear constants, we can use minus. And IPOPT's advantage is few function evaluations compared to GRG and SQP. Some rules, which I think you can read this in your own time. I think with this I can conclude the nonlinear part of the course. And if there's any questions, please send me an email or message. Thank you.